So lately we've been talking about what rational functions are, right? Rational expressions, rational equations, how to solve them, how to simplify them, what NPVs are, all this stuff. So in this video, we're going to talk about graphing rational functions and how we can apply everything we've learned into creating graphs for these things. So remember, rational functions or rational expressions are instances where we have the variable on the bottom of our fraction. So for example, 1 over x, that's a rational expression, or 5 over x plus 2. Okay, and all of these things we can say y equals this thing. So y equals 1 over x, y equals 5 over x plus 2. And this will, like both of these graphs, these rational functions, will take on kind of odd shapes that I'm going to talk about in this video. Different from the classic parabolas or lines or sine waves that we've been seeing. So graphing rational functions, well, whenever we're graphing things that we're kind of unfamiliar with, I always like to make a table of values because it lets me see kind of patterns in the graph and the values as the x values change. So let's take the simplest case, y equals 1 over x. Okay, this is kind of the basis for all of our rational functions that we're going to base our transformation on. So if left side is x, the right side we're going to go 1 over x. Okay, I always like to start at 1, right? That's kind of my basis for all of my graphing. So let's say x was equal to 1. Well, when x is 1, y, or 1 over x, will be 1 over 1, which is also 1. So I'm just going to put that right here. X is 1 here, x is 1 here. Then that means my point will be right there. Okay, now let's say x is 2. Or no, let's go negative 1 actually. So negative 1, 1 over negative 1 will also be negative 1. So we can kind of see it's flipped there. Now if x is 2, 1 over x will be 1 over 2, which is 0.5. So that'll be x is 2, y is going to be 0.5 right there. And we'll see that if x is negative 2, this will be negative 0.5. So if our x is negative, it's just the negative version of what it was before. So we can see how it's kind of flipped. And let's say our x in our table of values is negative, or let's say positive a half, so 0.5. This will be 1 over 0.5, which is 2. Right, so 0.5, this will be 2. And it's going to be the same case here. If it's 0.5, it's going to be 2 for the negatives. Okay, so if it is negative 0.5, this will be negative 2. And now let's do, well, I scaled it so it goes to 6 in the x-axis. So let's go, what is the y value when x is 6? Well, this will be 1 over 6. 1 over 6 is about 0.17. So it'll be just under 2, or just under 0.2. So this is 1, this is 0.5, it'll be about there. Okay, and the same thing here for the negatives. So this will be negative 6, it'll be negative 0.17. Okay, so let's just kind of think about it here. We see that it kind of flattens out along this x-axis here. So if we connect all these dots, we're going to see that it's going to pass through all these points and kind of approach these x and y axes here. We kind of see the same thing here. And the reason for this, actually I drew that bad. I'm kind of a perfectionist with my graphing, so bear with me here. That looks a little nicer. So the reason for this is if we have, let's say we were trying to figure out where this function equaled, this function equaled 0, for example. So let's say we're saying 1 over x equals 0. Well, that means that we're trying to find some value x where if we take 1 and we divide it by x, we're going to get 0. Well, even if you take something that's infinitely large, 1 over infinity, this still won't equal 0. It'll be 0.00000 with an infinite number of zeros, but it still will have that 1 at the end. It's not going to be exactly 0. That's impossible. So this is called an asymptote. Okay, an asymptote is basically a line that a graph never meets. So rational functions have an asymptote at on the x-axis, a horizontal asymptote, and a vertical asymptote. And typically they'll be at 0 and 0, which is convenient. But that's not always the case, as we'll see with our transformations, okay? So the reason that x can never equal 0 is because if y is 1 over x, well then y will be 1 over 0, and 1 over 0 is undefined, right? It's a infinitely large or infinitely small number. So we can't have that either on our graph. It's undefined at that point, x equals 0. So the domain and range are limited, right? We can have any real x, any real y, except neither of them can be 0 for y equals 1 over x. Now let's talk about transformations. So just like we did with parabolas and sine, cosine waves, what if we had y equals 1 over x plus 5? Well, this is the same as y equals 1 over x, except we have this plus 5 here, meaning that this graph, y equals 1 over x, is going to be shifted every point 5 to the left. Because remember, if this number here is positive, plus 5, that's like x minus negative 5. So this negative 5 is really what we're looking at, because it's typically 1 over x minus a constant. Okay, so if it's 1 over x plus something, we're shifting the negative value of that constant, right? So we're going to the left. What if our function was y equals 2 over x? Well, this 2 here, this is like y equals 1 over x, right, times 2. So it's like y equals 1 over x, except for every point on y equals 1 over x, we're multiplying its height by 2. So on this graph, when x was 1, this would now be 2 instead of 1. This would now be 4. This would now be 1, right? And everything would be kind of steeper. Okay, so things are going to ascend steeper if our graph is y equals 2 over x. That's the transformation there. That's the vertical stretch. Okay, what if it was y equals 1 over x plus 1? Okay, well, this plus 1 just takes every point on the original y equals 1 over x, which we have graphed up here, and we increase it by 1. So instead of this coordinate here being 1 and 1, it'll be 1 and 2. This coordinate won't be 2 and 0.5, it'll be 2 and 1.5. Okay, so every coordinate's just shifting 1 unit up. It's not changing shape, it's not stretching or anything, it's just moving vertically. Okay, so it's kind of like the opposite of x plus 5, right? Instead of shifting horizontally, we're shifting vertically. So let's take a look at some examples. Graph the function f of x equals 3x minus 3 over x squared minus x. So f of x equals 3x minus 3 over x squared minus x. We're going to utilize our skills now with factoring and simplifying rational expressions. So on the top, we can factor out a 3. We'll get 3 times x minus 1. On the bottom, factor out an x. We'll get x times x minus 1. So you'll see that these x minus 1s will cancel. We're just left with 3 over x. Okay. And what we're going to have here is a non-permissible value at x equals 1, right, and x equals 0. So there's going to be a hole there. But once we simplify this graph, it's going to look a lot like 3 over x. So if we draw our non-permissive values, our holes at x equals 0 and x equals 1, I'll write that to the side here. NPVs, x equals 0 and 1. Okay, we're going to graph y equals 3 over x. Okay, so if our asymptotes, right, they're not shifted. So our axes for asymptotes are going to be at 0 and 0. Okay, so for 3 over x, we're going to move over 1, and we're going to go up 3 now, because 3 over 1 is just 3. Okay, 3 over 2 is 1.5, so that'll be here. 3 over, this will be right there. 3 over 3 is 1, so that'll be right there. Right, so we're just kind of graphing various points on here, and it's going to look something like this. All right, going to flatten out there. And we can do the same thing on the bottom. So if it's 3 over x, 3 over negative 1, that's going to be negative 3. So it's going to be right there. Okay, 3 over negative 3 is negative 1. So we'll go right there. And then 3 over negative 2, that's going to be negative 1.5. So it's going to be right there. We can kind of draw our graph right there. Okay, that's what our graph's going to look like. And remember, we can't forget about our NPVs because the function isn't y equals 3 over x. It's y equals 3 over x with NPVs at 0 and positive 1. Right, so clearly there's going to be an NPV at 0. We don't need to draw a hole for that. We know that the asymptote covers it. Okay, but for positive 1, the function doesn't exist at x equals 1, so we're going to have to draw a hole right here. The function doesn't exist right there. Because if you were to put in 1 for x, you'd get 3 times 1 minus 3 over 1 squared minus 1. This will be 0 over 0, right? This won't exist. So after you simplify, you have to make sure that you're not forgetting about your non-permissible values. Okay, so the asymptotes for this will be at y equals 0, x equals 0, NPVs at x equals 1, and it resembles the function y equals 3 over x. Determine the transformations that the graph y equals 1 over x undergoes to become y equals 3 over x plus 2, or x minus 2 plus 5. So y equals 3 over x minus 2 plus 5. Well, we know this plus 5 here is a vertical translation. So I write vertical translation of 5 units up, right, because it's positive 5. X minus 2, this minus here means that we're moving to the right by 2 units, so I'll write horizontal translation of 2 units right, because it's in minus 2. And the last number here is this 3 on top. So I'll write vertical stretch, or just VS, of factor, I guess, of 3. So it's going to be 3 times as tall as y equals 1 over x. Okay, at certain points. It's not always going to be 3 times as tall, but we're just taking the original y equals 1 over x and multiplying every coordinate y value on there by a factor of 3. Okay, accurately graph the function h of t equals 5x minus 2 over x plus 1. So 5x minus 2 over x plus 1. State any asymptotes and describe the end behavior. So remember, the asymptotes is just the new axes that we create after we find the NPVs, like what the denominator can equal. And describe the end behavior. That's just where the function goes as x gets really big or really small. So where the function goes as we go to the left or to the right. So first, let's kind of simplify this. We're not used to seeing this type of linear term on the top because typically it's like 3 over x plus 1, right? Or something like that. But now we have an x on the top and the bottom. What do we do there? Well, remember, in the questions we're used to, let's say we had y equals 5 over x plus 2 or something. This plus 2 is a constant. So we have a rational expression right here adding a constant. So how can we get this up here into that form? Well, see how these terms both have an x in them? If we can somehow find a way to cancel those x's, we're going to just be left with this 5. So what we do is we say, okay, this is the same as y equals, we still have this 5 here, but we want this 5 to multiply into x plus 1, so we can cancel these two and be left with the 5. Okay, now the only issue with that is the top isn't 5x minus 2 anymore. Right, the top now, it's still 5x. This is still 5x, but this is plus 5 over x plus 1. So we have to add some term beside it so that when we add it to 5x plus 5, we get minus 2 instead of 5. So we have to think, okay, we have the 5x, which is good. We have the x plus 1 on the bottom, which is good. But we want this plus 5 to become a minus 2. So to go from 5 to minus 2, we have to subtract 7 over x plus 1. 7 over x plus 1. Right? Because if we had 5x plus 5 on the top here, and we subtract 7, this will just be 5x minus 2 over x plus 1, which is what we originally had. So this is a super tricky way to manipulate the equation so that it's in a form that we can graph. So now that we know we have to subtract 7 over x plus 1, now we can cancel these x plus 1s, right? And we're just left with 5 here minus 7 over x plus 1. And to get it in the form we're used to seeing, we just put the 7 over x plus 1 first plus 5. And remember, this plus 5, that's the vertical shift, the vertical translation. So now this is something that we're used to seeing, and it's a completely equivalent way of writing it. Okay, so now we know where our new asymptotes are going to be. We know our vertical asymptote is going to be at x equals -1 because it shifted to the left by 1 unit. So I'll just draw that here. Okay, and we know that that plus 5 at the end means that the y value, the y asymptote, horizontal, is going to be at x equals 5. So those are our new kind of axes for the asymptotes. And now when we're thinking -7 over x plus 1 plus 5, instead of going to the right and going up, we're going to go to the right and go down. So every unit, for the first one, we're going to move over to the right, we're going to go down 7. So right now it's at +5, we're going to end up at -2. Okay, and we could plot all the points we wanted, but the main idea is that it's going to kind of flatten out like this. It's going to look like that. We could come up with all the coordinates we wanted, but the main idea is that we find the axes with the asymptotes, and we graph it like we always do. So this negative means it's flipped. This 7 means it's expanded by a factor of 7, right? And you would do the same on the top. I didn't give myself enough room on the scaling, but you get the idea, right? So you would just plot these coordinates like we would always do. So state the asymptotes, we already did. Describe the end behavior. Well, the end behavior is just where the function goes as x gets really big or small. And you can see as it goes to the left and to the right, it kind of flattens out to y equals 5. So your answer for the end behavior would say, as x approaches positive or negative infinity, the y value, right, y would approach the value of 5. It would take on the value of 5. Okay, so that's kind of like the main idea. There's not really much more you can do in terms of asking like harder questions, how to graph these. The hardest kind of question would definitely be the last one we did, right, where we have a linear term on the top and the bottom. We have to do that manipulation, but just remember, if this is a 5 and this is a 1 in front of the x, your constant that you'll get will always be 5 because you want to get it so the 5 is factored out and you have x plus 1 on the top and the bottom. So it cancels. You're trying to figure out what you have to add or subtract to make it equal the original function value. Okay, just a bit of manipulation there. If you don't understand, go back or drop a comment, shoot me a message, all that good stuff, and I'll be sure to answer your questions, okay? Thanks so much for watching, and I hope you have a great day.